Okay, we have a look now at photometry. Now, photometry, as it says here, is the measurement of photons, whereas spectroscopy, I'll say that probably, spectrometry is measuring and using the spectrum. This one uses individual photons to determine things about, characteristics about a star. Okay, now, firstly, the understanding from our preliminary course that as light goes away from a source, it gets, sorry, it's got to go back, it gets duller. So we have a way of measuring brightness, which we call magnitude. And this magnitude scale has been standardized, and the standardization is shown here down below. We have decided that a magnitude change by 5 would mean a change of factor of brightness by 100. So if I have a magnitude, which we'll call the visual magnitude, as equaling 0, and we have another object which has a visual magnitude of 5, then the first object, one of the objects, is 100 times brighter than the other. We use this standard candle, as it's called, just to make sure that we have a metric system that works. We will also use numbers which are smaller to be brighter. Okay. So there is our standardized set of numbers. That makes that we have no arbitrary use of these scales, that we definitely have a metric system. Okay, so going on there. Right. So we, as already known, we have apparent and absolute magnitudes. So let's just make sure that we are quite familiar with the two terms. The apparent, firstly. The apparent magnitude is the brightness of a star as it appears to the observer on Earth. So it's the brightness of a star as it appears to the observer. And we, as you know, use a lowercase m. The rest of this definition here is just explaining a bit more about it, that it's not a true measure of brightness, it's only a measure of how brightness it appears to the observer. And we always use the idea that if we have a candle very close to our face, it will appear extraordinarily bright. Okay. Oops, sorry, going sideways, wrong way. Now the brightness scale, as you can see here, is open-ended, but we have 30 up the top here as the ones that we are used to, 30 and minus 30. The reason being that we have these two here is these are the two brightest, that's the brightest thing in the sky, which is the sun, and it's minus 28. So we don't really need a scale that goes anything more than minus 30. Remember, negative numbers are bright and positive numbers are dim. So we can see really the limit to our naked eye is 6 here. So we can see anything up to a magnitude of 6, and that's really quite dim. The Venus, as you can see here, is minus 4.4, and the full moon is minus 12 on a very, very clear night. Okay. So going back, oops, sorry, I keep on going the wrong way. I've got to find where's the absolute magnitude? This one. Okay, I'll just get rid of that. I'm having a bit difficult. I'll just pause here while I work. Okay, I found the slide. It was out of order. Now, the second of our magnitudes is the absolute magnitude. Now, the absolute magnitude, as we know, is a standard brightness. We can consider it to be the true brightness of the star. And to standardize the comparison, we measure it. We say that it's the apparent brightness when we are standing 10 parsecs from a star. It's a true measure of this brightness, but once again, we have to stand 10 parsecs from a star, which is nearly impossible. So our biggest problem in astronomy is to try and work out what absolute magnitudes of stars are. Because once we know both the apparent magnitude, oops, the wrong colour, the apparent magnitude, still the wrong colour, yeah, we can see it now, and the absolute magnitude, we can subtract them. That's called a distance modulus. If we divide by 5 and raise it to the power of 10 and then multiply it by 10, that equals the distance. So it's a quick and easy way of working out the distances around the universe. But we need to know both of these values. So going back now I can go back to these. We remember that our definition of the magnitude scale was that a difference of 5 means it's 100 times as bright. Okay. Now, why did we do that? It's just a mathematical construct. If we were to work out what a difference of 1 would be, if it's a times, it's a fifth root. So a difference of 1 would be 2.5 times as bright. So for every difference of 1 magnitude, it's 2.5. It's not exactly 2.5, it's 2.512, which is the fifth root of 100, but we can get rid of those numbers there. Okay. So just moving on, if I can get that to work, and go forward. Yeah. Right, yeah. If we have a look at these two stars here, okay, this star here has an apparent brightness or apparent magnitude of 0.2. So that's negative, sorry, did I say 0.2? 2.0. Okay. This one here is plus 1. So the change in brightness, the difference in brightness is 3. It doesn't matter which way you do it. And remember, for every one change, it's 2.5 times as bright. So it's 2.5 times 2.5 times 2.5, which is 16. 2.5 is not exactly, 2.5 cubed is not exactly 16. It's 16 with decimals, but it's approximately 16. So this star up here, the brighter one, is 16 times as bright as this star just here. Okay, if you can see that little star just there, that one there is 16 times brighter than it. It appears because these are apparent magnitudes. So for every one, it's 2.5 times, so it's 2.5 times as bright. Okay. Now we can probably we can use this formula here, which says that this is the comparison of brightness, how many times bright one is to the other, is 2.5 to the difference. So a few moments ago we said that the comparative brightness was this was negative, that was 1.0 or something. This was minus 2. So when you subtracted them, you got it up to 3. Sorry, I got that wrong way around. It was 1.0 minus negative 2.0, which equaled 3. It doesn't matter. We should only just discover which is the difference, and we'll take it as a positive difference. Okay, so if we had the first star here, let's have star A as its m equaling 2, and B its m equals negative 2, then we just work out the difference between them. Now you can subtract minus 2 will give you minus 4, or if you say 2 take negative 2, you'll get 4. We'll choose the positive value rather than the negative because it's easier to say one is 15 times brighter than the other, or one is 100 times brighter than the other, rather than saying one is 1/100th the brightness of the other. So if the difference is 4, so just rubbing that out, still taking that rubber, got it. Okay. Say the difference was 4, then it's 2.5 or 2.5 to the power of 4. So you'd have 2.5 times 2.5 times 2.5 times 2.5, and if we would calculate that, that's approximately equal to, I'm saying that was 16 there, 16 times 2.5, yeah, we'll say about 50 times as bright. Okay. Now, this 2.5 is only an approximation. We know it's not exactly, it's 2.5 and a bit. And the reason is it's the fifth root of 100. So this is the actual formula right down here that we are given on our formula sheet to compare brightnesses. And we get the 100 to the 1/5. That's the fifth root there of 100. Okay? So this is the exact formula, and this is a quick ready reckoner formula. Remember, A and B, this little fraction in front here, is just how bright one is compared to the other. Okay? So don't overly worry about the A's and the B's. Always the number up here, the difference of the moduluses, the difference of the magnitude, should always just be a positive number, and that means one is brighter than the other. Okay, so moving on. Okay, now we already know these magnitudes for distance here. This is the distance modulus formula that we use when we want to find it. Find the distance. We memorise that, otherwise we have to rearrange these formulas down below. The logs in both of these formulas are log to the base 10, and we already know that m is the apparent and capital M is the absolute absolute magnitude. Okay. Spectroscopic parallax is a play on words using the word parallax. Now, parallax, already we've discovered the trig parallax. The trig parallax says the distance is 1 on P, where P is a parallax angle. And that's to do with the relative shift of a star as the Earth goes around. There's the Sun, and the Earth goes from one point to another. And then we look at this star over here from this point, and we see this star moves, and this star moves here. So remember that the parallax angle was that angle there. So it's a play on words with this parallax, because that is a trigonometric parallax. Parallax is an object appears to move. Spectroscopic parallax is a way of using a star's spectrum or a photometry to determine the distance. And the simple process is we take a star's spectrum, tick, or use the photometer to do it. We determine the absolute magnitude, and a few moments ago we did the photometry of the Pleiades, and that most likely is the visual magnitude. And then we determine the star's temperature. Now we can do it two ways. We can do it by Wien's law, okay, which means we know the lambda max, or we could use, if we're doing photometry, we can find B minus V and then use it to find the temperature in Kelvin. And we also work out the star's luminosity class, because we need to know what type of star it is, whether it be a main sequence, which means it's on the main sequence, or it could be a red giant up here, this is a Hertzsprung-Russell diagram, or a white dwarf, and so on, okay? Because that tells us what type of star it is. And we use the thickness of the absorption line because luminosity class is to do with density. We then use a Hertzsprung-Russell diagram, and we can determine from the Hertzsprung-Russell diagram the absolute magnitude. Okay? Once we've got little m, the apparent magnitude, and the absolute magnitude, we can then use the distance modulus formula, and we found the distance in parsecs. Okay? So that's the spectroscopic parallax. So let's use spectroscopic parallax to work out this star here. Oops, go back. Okay. So there's a spectrum of a star that we've got. Okay. Now we can work out its temperature by finding lambda max. Now lambda max is up here. So there's lambda max. There's the peak. So this is lambda max down here. And that equals, if we read it off, as 4,850 angstroms, which, remember, an angstrom is a way of writing nanometers to four significant figures. So this equals 480, we just drop off that last one, nanometers. We use Wien's law up here to determine its temperature. So that temperature would be, instead of lambda max down here, we read 4 485 by 10 to the minus 9, which is nano. And when we shove that in, we can then calculate the temperature. So the temperature is 5,980. Okay. Now going back, if I get this to go back, yep, we can use the thickness of the lines to determine what luminosity class. So this is the actual thickness of the lines down here. So when we actually view this spectrum as a photographic plate, the lines are this thick. So if it was a class 1 star, which is a bright supergiant, they would be this thick. If they were a main sequence star, they'll be that thick. This would be the broadness of a number 2 star, which is just a luminous supergiant. This is just a giant. Okay, so we can, by looking at the thickness of these lines, we can work out and determine that it must be a main sequence star. So we now know the temperature and the luminosity. It is a 5,900 or 6,000, and we can now plot it on this line here, this Hertzsprung-Russell diagram. Now, it would have been much easier had I got a B minus V index, because down here, if I could get that to just put that on. Oh, come on, go yellow, because we can't see it. But down here is the B minus V. Now, B minus V, as you can see on this scale here, is linear. And if we use photometry, it's not working there, photometry, then we can determine B minus V, and then we can use a graph to work out the temperature in Kelvin. So it's much easier to work with, and we could have said, okay, the B minus V index was here, we could have gone up here. But we know that the temperature, we have to use temperature this time, so we've got to go up the top here, where's temperature, and we said it was 5,980, so we got it down here. So there is a plot, and it's a main sequence star, so I know that there is our star. Reading sideways on this Hertzsprung-Russell diagram, we can work out its absolute magnitude as 0.5. Sorry, as 5, not 0.5. So we now know that its absolute magnitude is plus 5. Now, do we know its apparent magnitude? Well, where do we find that? Let's go back. Whoops, it's going back the wrong way. Going back, the spectroscope found the actual apparent magnitude as 7.5 here. Okay, so now we know the following data, and we can just place it into this as 7.5 up here. So 7.5 there, and 5 there. Shove it into this formula here, we can get the distance in parsecs. So using this method, this is called the spectroscopic parallax. I think I spelled spectroscopic, got it wrong. Okay, it doesn't matter if we use photometry, it's still called spectroscopic parallax. Okay, thank you very much.